Here we are talking about radiant transfer for a single surface. This is Chapter 4, Material of Solar Energy Conversion Systems. And when we're talking about radiant transfer, we're essentially talking about heat. That would be energy transferred in time. You're looking at the symbol Q for Q dot for watts. And if we were to turn that into an intensive variable, watts per square meter, we would use a lowercase q. On page 81, you'll see equation 411. That is going to be the general equation for Q in terms of radiosity. We just talked about radiosity last lecture, and radiosity is defined in terms of energy leaving a surface. In this case, it's surface I. We have the area of the surface, A, times the radiosity J, and what we're going to do is we're going to take out the role of the sun from that, and the sun again is the input energy G, the irradiance input upon surface I. Now, if we take out those values, what we have is the heat transfer, the radiant heat that is leaving surface I. And so when I want to think about that in a quantitative fashion, what I do is a heat diagram or a thermal circuit for radiative transfer, which you'll see in figure 4.3 in the textbook. On the left, you have the energy of the black body for surface I. On the right of that circuit diagram, you have the radiosity of surface J, or surface I. And in between, you'll see what looks like a normal electrical resistor. Well, it's a thermal resistor here. And what we're describing is the surface resistance, Rs. The surface resistance of surface I, which is going to be 1 minus the admittance of I. Now we know that 1 minus the admittance is going to be rho, so the reflectance, divided by the admittance of the surface times the surface area. So here we're describing a single surface, and each one of these guys, this right here, this right here and right here are two nodes connected by a resistor. Physically, it's just the same surface, but we have this diagram to show that there is some sort of resistance to light being emitted from the surface I. Now, everything that we're doing is more interesting when we have more than one surface, and we will frequently be talking about two surfaces for this lecture. When I have two surfaces, clearly I'm going to have multiple resistances. So let's do a sketch of, first, how does light interact between two surfaces. I'm going to draw two parallel surfaces, and using the diagrammatic scheme that we started in the textbook. So I'll have surface 1 right here, surface I right here, surface J on the right, where the temperature of surface I is going to be greater than the surface temperature of surface G. They're both going to be surfaces in local equilibrium with their surroundings, so that Kirchhoff's law is going to be valid. Now if I draw the diagram, we're going to have light being emitted from surface I with an admittance epsilon for surface I. The light will hit surface J, and we're going to say some of that light, long wave light, is going to be reflected. That is going to be the reflectance of surface J, and the remainder is absorbed by surface J as well. But surface J is going to glow as well, and so it has its own admittance term, and the reflectance is tied to the reflectance of surface I. So the energy emitted from surface J is reflected by surface I and partially absorbed by I. Now let's do that again using that thermal circuit diagram. So I'll have my two nodes for the black body emittance, which is going to be scaled down to the radiosity, J, and between them I'll have some sort of radiant surface resistance, which we just described. Now I'll do the same thing for surface J. Okay. Oops, I wanted to point out that the intrinsic properties of the surface are going to be represented by Rs, and those are the phenomena that will make the surface gray, a gray surface rather than a black body or a white body. So here I have over on our right the two nodes for surface J, the black body behavior, and we know we're not going to have a black body behavior, it's going to be diminished, and so we use that circuit diagram to describe that in terms of the radiosity. Because I have a higher temperature surface on the left, surface I, heat will be propagating from left to right. There's my Q with an arrow showing the directionality of that radiant heat flow. Remember, this is light. And I'm going to have some resistance between those two surfaces. That's that red resistance between the nodes of radiosity for I and radiosity for J. I can describe that radiant resistance in terms of Rij, and you're going to see 1 over the area divided by the view factor. View factor is a new term that we're introducing here. You'll see it described on page 83, and we have an equation 416 where the view factor is the irradiance, that's the light incident on surface J coming in from surface I, which is why I've written specifically Fij, divided by the total radiant excidence from surface I. So all of the light that comes from surface I, only a portion of it is going to be accepted by surface J. Okay? And if Fij, the view factor from I to J, is defined, and if they're not perfectly parallel surfaces to each other, let's say that they are different surfaces at slightly different angles, then they're definitely not going to have the same view factor with each other, which is saying that they're not communicating perfectly with one another. Some light is escaping out into space, and it's scaling down our values. Now, the view factor itself, if we break it down, is a combination of what we would call the cosine projection effect and the inverse square law. So the inverse square law we're becoming more and more familiar with. That's how light spreads out with distance to the square. And we have a decrease in intensity from the source to the receiving end because light is being spread out in all directions. The cosine projection effect is a new term to us. We should do some reading on that in the textbook to help follow along with this. But I'm going to draw a diagram to describe the cosine projection effect because it's a big macro effect happening between the sun and the earth. I draw the sun, I draw the earth, I do my schematic diagram of a beam of light from the sun being emitted. It's going to be incident upon the surface of the earth, and so I'm going to draw a tangent for what is the surface that is horizontal to the earth. You could think of it as like a ping pong table standing up on the surface of the earth. Now, if I were to draw a normal vector, a vector perpendicular to that ping pong table surface, I will be pointing up to what we would call the zenith, and the angle between the zenith and the beam of light would be the zenith angle. And that you're seeing a theta sub z symbol for the zenith angle. And we're going to build on that because light and the intensity of light is inversely proportional to what we're going to call the angle or the cosine of the angle of incidence. So the cosine of the angle of incidence, well, the first question we ask is, what is the angle of incidence? And the zenith angle is a version of the angle of incidence. If I have a flat surface and I have a normal, a vector pointing normal to that surface, the angle between that vertical normal, as I've drawn it right now, and the beam coming in, incident, is going to be called the angle of incidence. and the cosine of that is going to be a value from 0 to 1, right? The combination of the angle of incidence and the inverse square law gives us a view factor from the Sun to the Earth that is 4.5 times 10 to the minus 10, which effectively is 0, right? Very, very small. And yet we still get an abundant energy source from the Sun. So view factor is important. It is proportional, or it is defined in terms of the cosine projection effect and the inverse square law. The actual view factor for the Sun, as we calculate it, is a very, very small number, and yet we still get a lot of energy from the Sun. Now, if I'm thinking about this, about what a solar panel really does, well, I have a solar panel at a much more earthly scale within what we call the sky dome. That's that big pancake of air that is above our solar collector, and which is all emitting light during the daytime in addition to the beam of light from the sky. And it's basically like a big old bubble enclosing a solar panel, which is a type of convex surface. That will become important later. The view factor can have a couple of special cases, right? The view factor where I have parallel plates, like we just sketched originally. A view factor where I have a sphere that is enclosing a much smaller convex surface, basically just like the sky dome that we had mentioned. In these two special cases, what we're saying is that the two surfaces, the inside of the sky dome and the outside of my solar panel, those two surfaces are communicating perfectly. The view factor will be effectively 1 at that point, as it would be between the internal surfaces of parallel plates. And in that rare scenario, the view factor for the two surfaces are, in fact, going to be equal to each other. Otherwise, they will not be equal to each other. Now, I'm going to work on what we're going to call a general case for radiant heat transfer. General cases are the types of scenarios where we have generally much more complicated equations. So stay tuned as we're going here. These are going to get to be some pretty dense equations. But we're going to go through the dense parts, and then ultimately we'll get into much more simplified versions that will help us to solve problems in our homework set. Let's start with equation 4.17 in the textbook. Now we're defining radiant transfer from surface I to surface J in terms of the radiosity of surface I minus the radiosity of surface J. And they're going to divide that by the resistance between surfaces I and J. And I define Rij as 1 over the area divided by the view factor. So but you'll notice that area of surface I is times Fij, whereas that equivalency is 1 over the area of surface J times Fji. A little nuance in there, but make sure you note that down. Now, 4.19 describes that the heat transfer from I to J is the negative of J to I. Right? That's pretty basic. We can understand that, but we want to make sure that we're understanding that heat transfer is going to be a directionality thing. And I can furthermore describe the heat transfer from I to J in terms of doing a rearrangement of Rij, a substitution as well. The area of surface I times the view factor between surface I and J times the radiosity of I minus the radiosity of surface J. and I've got the heat circuit, the thermal circuit diagram described. That's that same red circuit, red resistance diagram that you saw just a couple slides back. Okay, so on page 85, we are going to rewrite the radiant transfer Qij. And it's going to get pretty dense, right? So you're seeing up on the top on the numerator something very close to the Stefan Boltzmann, the Stefan Boltzmann representation for all the energy under the curve. But we're using two different surfaces at this point. We're using the surface temperature of I minus the surface temperature of J times the Stefan Boltzmann constant. That's going to tell us that that it is this thermal difference, this thermal gradient between the two surfaces that is driving heat. In the denominator, I've got three different values, and each one of those values is going to be associated with the resistance. So we'll have the surface resistance Rs of I first, right here, and then we're going to have the surface resistance of surface J on the right side, and between them we'll have that intermediate Rij resistance. Okay? This is a very nonlinear equation, and one thing that we're not including in here right just yet is HR, or the radiative heat transfer coefficient. So let's show how that fits in, because it's actually kind of important. The equation that you're seeing is, of course, very nonlinear, and we would like to linearize it. And one of the ways that we do that is through the radiative heat transfer coefficient, HR. HR actually linearizes a radiative transfer equation so that you get something that you would normally be familiar with in your textbook from a heat transfer class, which is the area of the surface times the heat transfer coefficient times Ti minus Tj. Much simpler. But then if we were to look under the hood at what HR is really representing, HR becomes, the heat transfer coefficient becomes the much more complicated equation. And so you're seeing me break down t to the fourth into parts, and you're seeing that in the denominator I've brought out AI of most of those equations. And so you're only seeing something a little more complicated over on the right hand side. But notice that the area term is no longer in the first two portions of the denominator. You're going to see that in equation 4.22 inside the textbook. Okay. Now let's get to those simplifications. I can simplify radiative transfer from that very complicated general case. I have two special cases that I described just a few minutes ago. The first case is where I have two parallel plates. They could be flat parallel plates, or they could be spherically layered plates. And in either case, the area of surface I is going to be effectively equal to the area of surface J, and the view factor will be equal to 1. We're going to see equation 4.23 there, where I have turned an extensive heat transfer term, capital Qi to J, divided it by area, and turned it into an intensive heat transfer term, which will be watts per square meter. And then you see a very similar variant of the radiant heat transfer equation on the left-hand side. Okay. I'm going to extract out of that equation the heat transfer coefficient from equation presented in the textbook from equation 4.24. And in doing so, I'm going to have linearized that problem. The second simplification is very relevant to solar energy conversion systems. It's the simplification where I have a very small convex shaped object that is embedded inside of a very large enclosure. And in that case, the area of my very small convex object is going to be much, much smaller than the area of the enclosure, such that the ratio of the two will approach 0, and the view factor, though, is still going to be equal to 1. And it's really that view factor equal to 1 that allows us to simplify our equations. So let's look at equation 4.25. Again, I'm going to turn an extensive variable into an intensive variable by dividing by area. And I have a very simple equation for radiative transfer, epsilon sigma t to the 4th I minus t to the 4th j. And my radiant transfer equation is similarly pretty simple compared to what we just seen. Now, why is this important? Why is this important to our problem solving? Because relative to the entirety of the enclosure of the sky as a sky dome, all solar energy conversion systems are small and convex. And so, in general, we can apply this type of simplified radiative transfer equation to the vast majority of our heat transfer questions for radiative transfer, which is really quite a relief when we go back and look at where we came from in terms of the general case. In that case, we have a very dense radiative transfer coefficient in equation 4.22, whereas here I have a much simpler one. Okay, so let's leave it at that. I recommend watching this video, taking pauses, breaks. We've gone through this pretty quickly, and take notes from the textbook. I think we've got a close parallel between what the textbook is talking about and what we just talked about in our notes. All right, thanks so much.